Okay, and let's continue with 7.5 with the vocabulary term exponential decay. This is when a quantity decreases by the same percent over equal time periods. So we can still use the exponential function to represent exponential decay, where a is positive, a greater than 0, and b is between 0 and 1. Okay, so to find the amount to which the quantity decays after t time periods, let's use the following model. Y equals a times the factor, decay factor, 1 minus r to the t power. So a here will be the initial amount, the beginning amount. R will be the amount, the rate of decay, and t will be the time period. And again, 1 minus r is your decay factor. And here's a mini proof for this model. If you begin with a certain amount, which we call the initial amount, and we subtract it by the amount of decreases, which is represented by the rate r times the initial amount, we can rewrite this as a times the decay factor of 1 minus r, where I factored out the a. So if you distributed this, a times 1, it's still a, and a times r is negative r times a. So that's where it comes from. So for year 1, we will begin with a, and we will multiply that by the decay factor 1 minus r to the first power, because it's for one period or 1 year. And after 2 years, we have to begin with where we left off with from last year, and then multiply that by another decay factor of 1 minus r to the first power. And then by using the product property, we can add 1 and 1 to get 2. And the base will be the same, a times the decay factor 1 minus r to the second power. So we can conclude that after t years, y can be represented as a times the decay factor 1 minus r to the t power. Okay, and here's a concept summary for exponential growth and decay. So for exponential growth and decay, we use the same exponential function, y equals a times b to the x power, but there's a different restriction for exponential growth. A must be positive and b must be greater than 1, and the graph would always curve from left to right and upwards. The growth is shown in this part of the graph, and it will always go through a point that crosses the y-axis. But on the other hand, for exponential decay, it means that there's some item that is exponentially decreasing at a really quick rate. So the restriction would be that a has to be positive and b would have to be between 0 and 1, meaning it must be a fractional amount. And the graph would always curve from left to right in a decreasing manner. Okay, so as x increases, y decreases. All right, and just to repeat again, as x increases, y increases. So this is how to interpret this graph, the growth, the decay. Okay, let's continue with the guided practice, part D. Tell whether the graph represents exponential growth or exponential decay. Well, it's very obvious. By looking at the graph, it's an exponential decay, okay, because it's curving from left to right in a downwards direction as x increases. And to write a rule for this, we need to look at the point 0, 5 and take the exponential function y equals a times b to the x power, and we're going to substitute in 0, 5. To determine what a is, which is 5. Okay, b to the 0 power is 1. So 1 times a is still a, which makes 5. Okay, I'm going to rewrite this as y equals 5 times b to the x power. And then I'm going to use this point to find out what b is. Then we can take the square root, and b is 2 fifths. Well, technically positive negative 2 fifths, but we're only concerned with the positive fraction because b needs to be positive in this case. So therefore y equals 5 times 2 fifths to the x power. Okay, for part E, you are to write an exponential function of the form y equals a times b to the x power whose graph passes through the given points. So I'm going to write this exponential function. Okay, I'm going to substitute 0, 1 in to look for the value of a. Okay, in this case, b to the 0 power is 1. A is still 1. Okay, I'm going to take the second point to find the value of b. So I'm going to substitute 1/4 in for y. I'm going to substitute 1 in for a. I'm going to substitute nothing in for b because I'm looking for b. And I'm going to substitute 2 in for x. So therefore I get b squared equals 1/4. And I need to take the square root on both sides. So b will be positive 1/2. Well, it's also negative, but we're not concerned with the negative value in this case. So to write the final exponential function, it will be y equals 1 times positive 1/2 to the x power, or simply just 1/2 to the x power. I highly recommend that you put parentheses around the fraction so it's clear that we're taking this fraction to the x power. The following word problem illustrates a real-life example of when exponential decay occurs. So here the half-life of a foul-smelling substance is 4 years. So I'm going to label that here. Okay, but before I continue on with the word problem, I would like to let you know that half-life means the time required for half the substance to decay. Okay, so if you have 8 ounces of this strange substance today, how much of it will you have after 20 years? Here's a formula that will help you in calculating the amount after 20 years with a half-life of 4 years. So 20 years, I'm going to label that here. Initial amount of 8 ounces, and we're looking for the new amount. Go ahead and plug in every single number into the formula. So A0 will be 8, and then times half to the 20 divided by 4. So after 20 years, with a half-life of 4 years, you'll end up with a 1/4 ounce of this strange substance. Okay, and this concludes the lesson.